Okay, good morning. Welcome to the today's class. Uh, Let us see that today is the lecture number 17. I hope so. No, 16. Okay, number 16. We have been discussing about finite state machines, right? So let us continue with the finite state machines. Uh, what we have seen previously. Let us recapitulate what we have seen in the previous class. We have talked about Mealy FSM. So, and in order to represent any digital system, we have used a finite number of states. And one way of representing the finite state machine is with the help of Mealy. According to the Mealy FSM, it says that whenever you write some particular state, okay, but I say something like this. We thought that whenever you talk about a state, whether we have to move forward, okay, or it should be there remains in the same state, that decided by the input signal. So this input is allowed. If the input is true or false, then we can move forward, or it can remain same state also by the input signal. Okay, and immediately after we need to mention its output also. Okay, so once it is the input is given for the particular input, the state can changes as well as the output also can be defined there. Okay, so this type of representation normally called as Mealy FSM. Okay, so here the present state, whatever the state that we are talking about, this is called a present state, is not depends on an output. Okay, so that's depending upon purely the input condition that we have applied. Another one is also there that is called Murray FSM. Murray FSM. So this is the topic of discussion today. So what is there here? Here we talk about the state. The state decide the output value. The state decide the output value. So if you are there a particular state, then automatically defines its output. Okay. Okay. This type of representation is called Murray FSM. So we have to go to the next state only with the help of the input. Only help of the input. Okay, we can go to the forward or it remains in the same state. It is possible with only the input. Okay, so the state of the system will define the output. Okay, so the purpose of the Mealy and Murray is one and the same. There is no doubt. To represent the digital system with the help of finite number of state, but two flavors are there in it. But one of the important thing to observe that if you're using the Murray FSM for digital system representation, it needs one state extra. One state extra. We need to find one extra state. One extra state. So let us see why one extra state is observed in Murray FSM. Right? Okay. The same example that I would like to take here in this Murray FSM as well, that is a sequencer detector need to detect 101 sequence by applying the input, and should produce an output whenever it detects 101 set from the input sequence. Okay, so let us write quickly to this one. Mealy FSM already we have seen. If you are there in the state number 1, state number 0, if 1 is there, then we have to move to the second state. If not, you have to be there. So at the moment, at the same time, we have to apply the output is 0 because 3 bits are not observed. So therefore, it will be there. The output value is equal to 0. In case of S1, if in case of input is equal to 0, for example, then remains in the same state because that input cannot affect the digital system. Okay. So here also the output is equal to 0 since we have not at all detected complete 3-bit of information. Similarly, we find that 1 we have detected here. We focus mainly on whether the next bit can be a logic 0 or the next bit can be a logic 1. So next bit is a logic 1. It is a valid bit only, but it is a 1. Since overlapping sequence required, from this bit onwards, we can start a new sequence. So already 1 is detected. Therefore, I would like to remains there in the same state. That is called 1 by 0 is the result. But for example, if 0 is the second input, then 0 is not a valid bit. But we can decide where to go by this entire sequence. So 10 is 10 is actually a valid sequence. Therefore, I can go to the next state called S2. Okay. So this state says that I have detected 10. What if you get a logic 1 or logic 0? If it is a logic 1, for example, so all the bits have been detected. From this bit onwards, we can start a new sequence. Therefore, what we can do that we have to go to the previous state. From this onwards, we start a new sequence, right? So when we apply the logic 1, we will move to the state S1 with output is equal to 1. If it is, for example, 0 is the third bit, the sequence is not at all detected, but somehow we have to move. What if the third bit is 0? So because the bit number 0 is not a valid bit, therefore I can start from the initial state, that is called 0 by 0. So this is how the Mealy representation that we have done, Mealy FSM that we have already seen there. Now the same detector is represented by Murray FSM. Let us see how can we do this one. Now, so the state S0, for example, immediately say what is its output that in that particular state. So initial state of the system is logic 0. Initial output of the system is logic 0. Why? Because in this initial state we are not able to complete the three bits. Okay, so just we have started one. That means we have only 1 bit of information. That means the state of the system always defines the output. Okay, unless otherwise 3 bits have been detected, has to be detected, then only we can say that output. Okay, now in this case, when we have logic 0 is an input, we should be remains in the same state, right? The same as that one. But we did not mention input by output relationship. Okay, so the present state decides the output. Okay, fine. What if logic 1 is there? It will go to the next state. That means that the logic 1 is detected in this particular state. But we also remember that the 3 bits have not been detected, therefore the output is equal to 0. So this is what the second case that we normally consider. Okay. So in the second state, we observe that 1 is detected. Okay, 1 is detected. So and a sequence of bits are coming, right? So what if the second bit is logic 0? What if the second bit is logic 1, for example? Okay. Yeah. So first consider logic 0. As I mentioned that logic 0 is not a valid bit in a given sequence. So our requirement is that 101 is required. So we can start the sequence with logic 1, right? But it is not started with logic 0. It started with, for example, logic 1. It started with logic 0, for example. Okay. So therefore, it's not a valid bit. That means I cannot start a new sequence. Actually, what the point is that, so I have this one, for example. Now I got that logic 0, we have got this one. Okay. Now this is compared with this one. For example, 101, it is compared with this. Okay. This sequence is compared with this sequence. Yes. This 10 sequence, whenever the second bit is equal to 0, that is satisfied, immediately it will go to the next state. Okay, that is called S2. Here also 3 bits have not detected. At this stage, only 2 bits have been detected. Therefore, the output is also 0. So therefore, the x is equal to 0 at this point. X is equal to 0 at this point. Right? What about 1, 1? So that means I'm saying that this is what the scenario, and it is 1, 1. So do we say that this sequence and this sequence is equal? No. But I can start a new sequence from here onwards. I can start a new sequence from here onwards. Okay, so I can start a new sequence from here onwards. Okay, that means I need to choose that the logic 1 state identification. So where logic 1 is identified. Okay, so as I mentioned that this is where logic 1 is identified. Logic 1 is identified. So therefore, immediately the signal will come, and therefore, if logic 1 is there, it comes back to the S1 state. Right? Agreed? Fine. Now, we say that 10 is detected here. Fine. Now, there is a possibility of the third bit can be 0, the third bit can be 1. Okay. Now, we want to detect logic 0, 1, but now we got the output is 100 is an output. So this is what the sequence so far we have got. So do we say that these two are equal? No, these two are not equal. These two are not equal. Then can we start a new sequence from this onwards? I can say that can we start a new sequence from this onwards? No, because it should start with logic 1. Or else can we start a new sequence from this onwards? No, it is also not possible. Therefore, what we have to do then? There is no possibility. If the sequence is not a valid sequence, bit is also not valid bit. Therefore, immediately it come back to the original position. Come back to the original position. If it is yeah, I'm sorry, forgot that this is not the place here, right? So this is actually absurd at this place. Extremely sorry for that. If it is logic 1, okay. So we are talking about S1. We didn't go for S2. S2. Now we have entered into the S2 state. Okay. Now this is what if it is the input is logic 0. For example, if it is a logic 1, if it is a logic 1, so for this is if, for example, if you consider this case, let us consider here is a 101. Is it true that the sequence is detected here or not? Yeah, the sequence is detected here. So both are equal. This both are equal. Therefore, we have to generate a new state called S3 state with an output is called 1. Right? So for this is the place where we have got that. Okay, so therefore this signal will go, that means the state it changes to S3 provided we have to apply logic 1. Clear? Now we should not wake into this state something like this. So when you are there in the S3 state also, that means what is the S3 state says that we have already detected 101 possibilities there. Maybe X, the input can be a sequence of bits, right? The input is a sequence of bits. So the fourth position also came into existence. Okay. So for example, there may be a possibility of logic 0 here, logic 0 here, sorry, logic 1 there. Logic 1 is here. Okay. So that means that I have 101 sequence, but now I got 1010. So the first case I'm talking about here. Okay. So can we start a new sequence from here onwards? Can we start a new sequence here onwards? No, not possible. But is it possible to start a new sequence from overlapping of these two? That's the question. Overlapping sequence can be possible to take. Yes, obviously we can take this one because 10 is a valid sequence here. 10 is a valid sequence here. Therefore, that means that we have already detected 10 sequence in a particular state. Which state that is happened there? As we have mentioned that here is one is identified, simple notation I'm writing, one detected. Here is 10 is detected. Here is 101 is detected at this point. So our requirement is that it has to go to 10 sequence state. So S2 is the relevant state for that. Okay, so therefore I should move to S2 state provided we have to apply logic 0. Right? Now, what if it is 1011? What it is 101? What it is 101? Can anybody guess where it has to go? Can anybody in the class can tell me what is where it has to go? Anyone from the class? 101, where it has to go? It is in S0 state, S1 or S2 or S3. Student, please respond. Any idea? That means the fourth bit is actually a, we got logic 1. From this bit onwards, can we start a new sequence? Yes, obviously we are able to start a new sequence from this onwards. Obviously we can start this one. So why? Because if it is a valid bit, we can start from this onwards. If it is not a valid bit, we need to go for backward. We need to go for backward. We have to check with respect to the previous one, is it possible or not? Right? So that means that so from this bit onwards, I can start a new sequence. Thank you. Thank you for your response. Yeah, it has to go to, one of our friends suggested that we have to go to S1 state. That means we have started a new sequence in the S1. Therefore, it has to go to S1 state. Okay, I'm writing here is S1 state. Okay, therefore, each and every state is defined properly. What if it is a positive volume? What is this a negative value? Or we can say that what if it is a logic 1? What if it is logic 0? The state table should not be vacant. Okay, so we have to say that for all possible input combinations. Okay, for each and every state, they have two possibilities according to the sequence detector, either logic 0 or logic 1. So each and every state need to be defined for every possible case. Agree? So therefore, you observe carefully. This is the state is extra state that we have got. Why we have an extra state here now? Because we have to define the state of a system, its output. Output is defined based on the present state. Okay, so therefore, obviously, the more hardware is required for the Moore representation. Some aspect of people will use the Moore, some aspect people try to use for merely FSM. Okay, so anyway, we have an option that Moore FSM is there. Then we need to write a Verilog program for that. Okay, so let's do that. So let us modeling up from Moore FSM. Modeling of Moore FSM, right? So the previously I have done that one. I copy that code and the relevant information only I want to change. Okay. So the digital system can be viewed as a combinational. Okay. So what is the table that we need to have? What is the state diagram? So it is simply a sequential circuit. The sequential circuit is represented by a combinational part as well as a sequence memory element. Okay, so the notations are also same. I'm following X and Y and clock and reset signals, something like this. And I can copy this state diagram in this one. Okay, I can copy this state diagram. Okay, now, so everything is same except something here. The clock reset and X output is equal to 1 down to 0 of Y, register present state and next state. For every positive edge of the clock, the present state is assigned by the next state. Yes, exactly the same code that is applicable here also. When the positive, whenever we find a, okay, I think we did wrong something here. Okay. Yeah. In the last class, we have not written correctly. I need to change this one. I'm sorry for that. Let me go and change this code. Okay. Okay. So there's a small change here we observe. Okay, here. See, we are talking about I'm talking about the previous Verilog programming. I didn't notice this. Here we observe that this particular block, what is this block we are talking about? This combinational block. Okay, this combinational block. So what is there in it? Therefore, this is the combinational block. Have got X is one input and the present state is one input, and it produce the output Y, and it will produce next state. This is what the combinational circuit is all about. Agreed? Now, this combinational circuit is modeled with the help of always statement. That's what I have followed. So always statement is used to realize, to describe this combinational block. Okay. So therefore, the output of the state is depends on output, or maybe these are the two outputs. Forget about whether it is a 2 size or 4 size, it doesn't matter. So the output of these two is depends on the inputs of this one, right? Whenever there is a change in X or whenever there is a change in the PS, automatically the output Y and next state will changes, right? So therefore, I forgot to write that here we have X as well. Here we have X as well. Okay. So that means this always statement always presents the sensitivity to the output variables. That means we have to mention the sensitivity list. What do you mean by a sensitivity list? The list of variables that can affect the output. Okay, obviously both inputs can affect the output signals. Okay, now, so now we would like to write some procedural statement. That procedural statement, we use case procedural statement. We are using case procedural statement. Okay, sometimes we can use if statement, sometimes we can use it for loop, whatever it may be, it is the case. But in this particular example, I have introduced a case statement. Okay, so therefore the case statement is depends on the state diagram. Okay, so therefore each and every state is represented by one case. This is the one case, S1 is S0 is one case, S1 is one case, S2 is another case. These are the different cases I need to consider. Okay, so fine. For example, if you are there in this present state called 0, 0, that means S0 state. Okay, so it is says that it is an S0 state. What has to happen if they're in the S0 state? For this S0 state, we should mention where, what is the next state we have to mention, and what is its value also. What is its output value also? Please remember that we should mention what is the next state. Sorry, we should mention what is the next state. So that means this is the line. What is the next state, and what is its output? That's what we are saying that. Okay. So that means that when the present state is observed here, we should mention what is the next state. Well, sorry, what is the next state? What is the output? Right. So if you want to say that this is what the next state, this is what the present state, that's depending upon input signal. That's depending upon input signal. Okay, that means we need to write something about the input signal. How do I write like this? So I can write something like this. Okay, now I can write I need to say that here we can start if x is equal to true, for example, if x is equal to true, if x is equal to true, what has to happen if we are there in the S0 state? As from the diagram, what we observe that in the S0 state, if you are there here, it is nothing but a 0, 0 condition, 0, 0 state. Okay. If input is, if x is equal to 1, for example, then it has to go to S1 state. Its coding is, its encoding is 0, 1, right? It has to go like this. I'm sorry, this is not the notation, right? So this is how. Right? If x is equal to, it has to go to S1 state. That means the next state should be, what is the next state? 0, 1 state. Yeah, if it is true, this is what happened. And we should mention the output also. Okay, the output is also y is equal to 1 bit of 0. Both need to be said. So therefore, if x is equal to 0, okay, if x is equal to 1, then we have to mention its output also y is equal to 0 here. So therefore, I have mentioned both cases. One is the next state, one is the output for x is equal to 0. For x is, sorry, for x is equal to 1. Okay. Okay. Now, so you observe that if statement I have written here, under the if statement, two statement I have written. Two statement I have written, right? Agreed? Two statement I have written. So in Verilog, when we have more than two statements, more than one statement, it is usual practice to write begin and end. Not usual practice, it is you should write begin and end statement. Agreed? Clear to all of you? Now, so that means x can possibility have a else statement. That means the x can be a logic 0. Then I can use else statement. And the else statement, where we have to go? We should be there, remains in the same state, right? X is equal to 0 for y, and one more thing is the output is also 0. That I can place this the same statement, but with different values, right? All of you, please correct the code previously that I have given there. Okay, then I can remove this one, but it should be remains in the same state. I want to remove this one. I want to place it properly. Is it clear to all of you? Please respond through the WhatsApp through chat box whether you have followed or not this statement. Please respond, students. Please respond. How I have written the case statement. If you are there in the present state, is yes not, what will happen? Yeah, thank you. Similarly, the remaining cases also we need to write. Okay, so I don't want to use this code again, and yeah, so how many times that I have to use this one? For 3 cases, for 3 states I need to write. Finally, I need to go for default statement, right? Okay. For the default statement, I can say that we would like to stay back in begin and end. I don't want to check anything here. For any other cases, the next state is equal to 2 bit of 0 0 and y is equal to 1 bit of 0. Okay, but I have to change here. So it is logic 1 here. It is 1 0. In the second case, the next state where it has to go, if x is equal to true from the state diagram, it remains in the same state. Okay, yeah, it remains in the same state. Output is also 0. If it is false, it has to move to the next state. So the move to the next state is 1 0. Please remember that this is a 1 0. I think I want to see the modifications here. Here it is 0 1, for example. Change here. The second case is also completed. The third case. In the third case, if x is equal to true, it has to go to previous state, right? Yeah, if it is 1, it has to go to previous state. What is the previous state here now? 0 1 is the previous state. Otherwise, it has to go to 0 0 state. But if it is a previous state, means we have to mention its output. Output is equal to logic 1 because the sequence is detected at this state. Right? That's it. So all of you, please modify this code something like this. Whatever the code that I have given previously is not the meaningful one somehow. Okay. So the same code that I want to copy there in the Moore FSM. So here, what is the modification I can do here? Anyone from the class can tell me? Can anyone tell me about this? Just to apply our concept here. Okay. Apply your concept. So we don't find any problem with the memory element, but there is a problem with the combinational part, right? So yes, this combinational part is also required. It contains two inputs, one x, the next one is the present state. This also produces y and next state, the 2-bit of next state, 2-bit of present input, right? So therefore, the always statements in stereo list is correct only, and I'm using the case statement that is also true. But what about the cases? Can anybody tell me what is the output of this one? How to write the case number 1? Anyone from the class, please respond. Please try to use your concept. So what we are doing here, we have an S0. What is it? S0 is the state. It produces the output is equal to 0. Immediately it will have the output is equal to 0. If x is equal to 0, what will happen? Sorry. If x is equal to 1, what will happen? If x is equal to 0, this is happening. Okay, x is equal to 0, this is happening. It is go to the S1 state with an output is equal to 0. Okay, this is what actually. So we focus on this one. So based on this particular diagram, can you define what is the state of 2-bit of 0, 0? S1 case diagram. Student, please respond. Anyone, can please type it on the chat box, otherwise no need to spell. If x is equal to 1, S1, else S2. Yeah, there should be a more constructive is advisable. Yeah, thanks for that feedback. Yeah, so here you observe when you're there in the present state, for example, S0, okay, the output is defined directly. That means that whenever we have there in the S0 state, okay, we have to put your output first of all. The y is equal to 0. Y is equal to 0. Agreed? 1 bit of 0. That is the first thing that you have to do. When you are there in the first state, S0 state, we have to define the output first of all. Now, depending upon the input, the next state will be decided. So, depending upon the input, depends on the input, the next state is defining, right? Therefore, I don't want to write only in the if statement. I concentrated more on next state, not on an output, right? So therefore, immediately I can remove the while statement here, right? Since in the if statement only one assignment statement, it is also not necessary to use the begin and end case. Okay, so it's simply this is what happening. Else, what is happening else? Else we have only this is the thing. I think it's better to write very adjacent to that, and this is also possible to write in this way. After the semicolon, we can write any statement. Clear? If you're in the state called S0, the output is defined by logic 0. Now, depending upon X input, the next state will be defined, decided, where we have to go in that one. Okay. Similarly, I have to use, for this one, I need to use y is equal to 1 bit of 0. Okay. We need to remove all these things. Okay. It's not required. So we have to place it here. Agreed. Similarly, not required all these things. Not required all these things. Just I'm rearranging the things, nothing else. In this state also, we are saying that the output y is equal to 1 bit of 0. But in this particular Murray FSM, we write it is a 1-1 cases also we have. So there y is equal to 1 bit of logic 1. Please remember that here is the logic 1. Output is logic 1. Okay. So if x is equal to true, where we have to go for the last case 0 అయితే s2 కి వెళ్ళాలి. What is s2? Next state is equal to 2 bit of 1 0, else ns is equal to 2 bit of, sorry, 1 అయితే 1 కి వెళ్ళాలి కదా. So it should be 1 0, but it should be 0 1. That's one state it has to go. Okay, so that's how we can write. For the default cases, the next state is equal to 0, output is also 0. It doesn't matter for that. Okay. Is it clear to all of you? Please respond. If you have any problem, then I will discuss that point. Just only thing is that the patience is required and you have to in a position to grasp that information. Okay. Very simple, nothing else. So each and level by level, step by step that I have discussed about it. So, and one more thing is that sorry for this one, we have to say that FSM underscore Murray, right, like this. So previous one is also Murray underscore melee. Sorry, FSM underscore melee. Yeah, this is what the today's class, and it is possible to write the test bench for it. Okay, so I will give you the hint for how to write the test bench based on X and clock and reset signals. Okay, you please try to write the test bit for it with the help of whatever the waveforms that I'm giving. Not it is. Okay, fine. Now, so let me say that. Let me give you this one. Okay, the end module is missing. Huh? Okay, right end module. Okay, fine. So the top level module is look like this. It has got input called X. We have a clock signal. We have a reset signal. And we want to produce an output, that's all. Is it clear to all of you? So what are required here for us? X is required, clock is required, reset is required. The positive reset makes the output is the content of the flip-flops equal to 0. So the positive, that means we take some positive signal here and make that value is equal to low, something like this. So at 0 instant of the time, RST is high, where 10 nanoseconds, for example, RST is equal to low. Agreed? Okay. Next, what about the clock? I can start my clock from here. 10, 20, 30. So we are talking about positive edge signals. Okay, we're talking about positive edge signals. Remember that each and every edge is at a 10 nanoseconds delay. Okay, that means here is a 20, 30, 40, 50, okay, 60, 70, 80, something like this, so on and so forth. Okay, we can start with for each and every edge we have 10 nanoseconds of the delay. This is all about the clock signal. And input X is required. Okay. So for all these cases, I want to write it as logic 0. Here is a logic 0. I want to put it logic 1 here, and then logic 0, logic 0. I think but I can give. So here something like this, and logic 0, and here is also logic 0, but it starts here with the logic 1. Logic 0 here. Again, logic 1. So this is what we can give. So that means I have given preferably for the positive edges of these things when they have given, and this is observed at this point. Okay, this time slot. This time slot also I have given this one, and this time slot I have given this input, and this time slot I have given this input, right? So these are the inputs that I am giving. Okay, so we have to generate the output for this. Okay, we have to generate the output for this. Okay, we have to write the test bench for it. Okay, so please try to do the test bench. With this, we have come to the end of almost the first unit, module number 1. We have discussed about all the concepts related to Verilog HDL, especially in the point of programming. So the theoretical aspects like data types used in Verilog HDL and operators that we use in Verilog HDL and some miscellaneous concepts I have posted in my channel. So please try to use that one. So whenever a time comes, then I will discuss the points. Okay. So we have a plenty of time is there in the lab sessions are also. Those points will be discussed in more and more detail in that classes, in that lab sessions. So we stop here today. If you have any queries, you please respond. If not, you can stop. You can leave the class. Okay, please wait. I need to take an attendance.